Intermolecular forces. This is kind of where we are going to now. So a couple just terminology issues. So far in this chapter, we have been talking about intramolecular forces. So this is kind of a new term. You can kind of see I've underlined the prefix here. So this is ionic bonding, covalent bonding, polar, nonpolar bonding, metallic bonding. These are the chemical bonds. These are the forces that hold the molecule together. What we're going to talk about are intermolecular forces. These are the forces that are between molecules. So you can think of intramolecular, so this within, as like your skeleton, your tendons, your muscle. This is what holds your body together. Whereas intermolecular forces, this in green, this is like friendships and relationships and, love and hate and all those kinds of things that you feel towards other people. That's the difference. And this is what we're going to be talking about in our notes today. So none of this that is anything that you need to have written down right here, but just to break an intramolecular force, to break a chemical bond, it requires a chemical change, right? This is the chemistry. This is setting things on fire, mixing them together, and we see color changes. Bonds are broken and new ones are formed. This is kind of your traditional chemistry. When we're talking about breaking intermolecular forces, these are physical changes. So we think of like boiling or melting or breaking something in half or something being sticky, dissolving. That's kind of what we're talking about, because we don't need to break atoms apart, right? If we're going to break water in half, we need to break the bonds holding the water together. For intermolecular forces, we just have to pull the water molecules away from each other, right? It's like separating magnets versus breaking the magnet into 1,000 different pieces. So it's a little bit easier to do. And this is what you really need to know for ultimately the test at the end are the different types of intermolecular forces. So the first one we're going to talk about are what are called London dispersion forces. Is it glitchy on your screen? Things are like coming in and out, or is it pretty smooth? Not smooth? All right, I'm working on it. So you don't need to write any of this stuff down. This is just kind of explaining what London dispersion forces are. So it's this idea that every molecule, every atom, there are electrons. And generally, if we look at this bottom left picture, the electrons are evenly distributed. And so as a result, when we look at the whole atom or the whole molecule, it's neutral. But electrons randomly move around. And so every now and then, you're going to have a situation like here in the bottom right-hand corner, where the electrons have kind of concentrated themselves. They've ganged up to one side of the molecule. And so you'll notice what you have here is, if you look on the left side, you have this abundance of negative charge. And on the right side, you have this positive charge. And so you get this kind of dipole action, right? This two-sided magnetic type of attraction. You have one side being negative, one side being positive. And so a London dispersion force is kind of just a natural occurrence that happens in all molecules. Again, you don't need to write any of this down right now. That creates this kind of momentary polarity. So just every now and then, temporarily, molecules turn into being nonpolar because the electrons just find themselves on one side of the atom. And what you get is you get this magnetic attraction between two molecules. And it's temporary, right? Because just as the electrons randomly moved to one side of the molecule, which caused this temporary tiny magnet, they'll move back again. They'll go back to being evenly distributed and going back to being neutral. And so as a result of this temporary polarity that kind of happens, the strength of a London force is the weakest. And this is what you really need to write down in your notes. What you really need to know is that London dispersion forces are the weakest of the intermolecular forces because the polarity is temporary. And so this force that happens, this is what causes molecules to stick together. Just like your muscles and your tendons within your body cause your limbs to stick together, right? The friendships that you have with other people is what causes you to stick together, right? This is the reason why long distance relationships in the end fail, because they are weakened by the distance. You only see each other on breaks, you only talk to each other every now and then, and just overall it's just a very weak relationship and you don't stick together very long. Same is true with London dispersion forces. Because they're temporary, these molecules don't stick together for very long. Now, the next step up, I jumped the gun a little bit. This is just a matter that all molecules have this. So even non-polar molecules, to a degree, have a little bit of this because they have electrons. London dispersion forces are caused by electrons. And so this last statement here, larger molecules have stronger London forces, is because there's more electrons. If you have more electrons, the molecules are going to stick together better than when you don't have a lot, right? This is a good example would be, think of like tar, like asphalt tar, the black sticky stuff. If you've ever had the chance to like play with it on the road or anything like that, when they first like put it down. Tar is a non-polar molecule, but it's so gigantic, it sticks together really well. Anyway, you don't need to know that, just kind of FYI. The next step up of intermolecular force are what are called dipole forces. Dipole forces are the exact same thing as London dispersion forces, except for the fact that it's permanent. So this buildup of electrons to one side of the molecule is always there. So in London forces, it happens just because of natural random motion. In polar molecules, this happens because of the difference of electronegativity, right? The bonds, the electronegative atoms, they're pulling the electrons towards themselves, and that's what creates the unbalance. And so that unbalance is always there, and so that separation of charge is always there, and so those molecules are always tiny little magnets that allow themselves to stick together. Okay. So the strength of dipole forces are kind of in the middle. So dipole forces, they are stronger than London forces because the poles are permanent. That's all. That's all you really need to know is that London forces are the weakest. Dipole forces are the next strongest, and then after that, we have the granddaddy of them all, hydrogen bonding. And this is a very special situation. This is a very special situation. You gotta have hydrogen. And the reason this is special is because hydrogen is special. Hydrogen only has one proton and one electron. There are no, here, let me just get through, there you go, so you can get this stuff written down. So there are no inner electrons. So the bond that hydrogen makes, that's where the electron is. The electron is not circling around in the lower energy levels. The electron hydrogen has is involved in the bond. And so when hydrogen is shared unevenly, so when hydrogen is involved in a polar bond, that electron is really, really far away from the nucleus. And so basically, for hydrogen, that one electron is all that it has to wear. And when it is involved in a polar bond, it's like that person is taking their clothes away. And so when hydrogen, that proton is just stuck out right in the middle. And so it creates this really unique charge separation. It creates this really unique, strong magnet. You get this very, very, very positive side and this very, very negative side. Now, this also only happens, and I should have highlighted this. This only happens when hydrogen is bonded to nitrogen, oxygen, or fluorine. Nitrogen, oxygen, or fluorine. Hydrogen must be bonded to them. Write that down. Hydrogen must be bonded to them, nitrogen, oxygen, fluorine, in order for this to happen. If you just have hydrogen and oxygen in the molecule, but they're not connected, you don't get hydrogen bonding. They have to be bonded together. And the reason is because nitrogen, oxygen, and fluorine, one, are the three most electronegative atoms on the periodic table, and two, they have lone pairs. And so that situation creates this unique situation, and hydrogen bonding is the strongest IMFer there is. Okay? So that's really all that you need to know. To kind of explain it a little bit better, I have this little picture that you can look at. And so here we have nitrogen bonded to hydrogen. So we have this highly electronegative atom in nitrogen and our hydrogen. This is a polar bond, and so the one electron from hydrogen is getting pulled to the nitrogen. And so it creates basically this exposed proton where the hydrogen is. And because nitrogen has this lone pair on top of it, well, opposites attract. And so you have this basically exposed proton coming into close proximity with this lone pair, these two electrons that are just floating out here. And what you get is this really, 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 really strong attraction. And so these two molecules stick together really, really well. And that's what hydrogen bonding is. So what you really need to know for the test is the types of intermolecular forces, so London forces, dipole forces, and hydrogen bonds. You need to know the relative strengths of all of these. So that London forces are the weakest. Hydrogen bonding is the strongest and kind of all in the middle. And you need to be able to look at a molecule and determine which intermolecular force goes with which molecule. And so here's this little flow chart that you can use for predicting. If the molecule is nonpolar, your only option is London dispersion forces. If the molecule is polar, basically what you're looking for is a hydrogen bonded to oxygen, nitrogen, or fluorine. If the answer is yes, then it's hydrogen bonding. If the answer is no, then it's dipole forces. So it's a pretty straightforward little chart for predicting which intermolecular force you have.